I'd like to start by thanking the organizers around and Shmuel. This has been really fun for me, and I really have learned a lot, and I appreciate all the effort you've put into it. I'm going to talk a little bit about some things that are going on in my lab, that work of a couple different PhD students supported by lots of things. Yeah, please. Yeah, be happy to. How's that? Better? Okay, fabulous. Please yell if I'm not loud enough. I'll try to be not. I feel like I'm being too loud. Okay, loud enough. I wanted to start with some pictures of Jay. I've only known Jay since 2005, and I searched back through my own history of photos, and they weren't really better than these. I actually thought this was kind of fun. Young version of Marone here, lots of different things, group of people. And I thought it'd be a useful background, but I actually wanted to say a few things about Jay, and I thought it'd be easier to say them in the context of a plot. I remember hearing last night about the fact that Jay makes these awesome plots, and this is one of them. You'll hear more about it, I think, a little bit later on from Eli. It's a log scale on one side, and it's something that's shear stress normalized by normal stress, but actually the normal stress has been already normalized here, so that's kind of interesting, I thought. It's normalized, but I didn't really want the data. I really wanted the plot. In fact, actually, now that I realize, I didn't really even want the scales. I wanted my own scales. So I thought it felt like it was useful to have a log plot to show what I wanted to show, because I think Jay is kind of one of those people that really is, super special. And I feel like mean all these things. And you can imagine the phase diagram that one could produce on this kind of thing. Just, we all know plenty of people who are sort of, up in this range here. They've done all kinds of things. They're very creative. There's very few people like Jay who just, bring us all together as a community. And I feel, especially me, because, look, I'm way outside of this field. And Jay, the first time I met him, he knew what I was doing, and he was interested in things. And just, yeah, okay. Thank you, Jay.
The x-axis is inverted. 0 is on the right side.
Thank you, yeah.
Another axis of humor.
Certainly, this is a projection onto 2D, okay? Yeah. Certainly multi-dimensional. Okay, so I want to talk about slow earthquakes, and I'm going to tell you about some things we've been doing in my lab related to friction experiments, and I'm going to tell you in particular about some stuff that shows how you can transition from stable sliding. This is a plot of stick-slip stress drop, and it might be more complicated than stick-slip in the end, but it is that kind of plot as a function of slip velocity. And what you can see is that the stress drop decreases systematically as a function of normal stress and slip velocity. And it does so in a way that's kind of, not too hard to understand if you get past some of the places where we've been as a group over the last 20 years or so. So that's kind of where I'm going. I'm going to tell you about some things that were done in 2 different places, and I'll get to that. One in my lab at Penn State, and then one at a lab that I was involved in helping construct something in as part of my sabbatical. In terms of the background, because I felt like it was kind of useful for me to do that, because I am so different than a lot of the people in this room, I wanted to give a kind of personal view of where things have come from in this field. And they start in many ways with this. I mean, this is not obviously the first time anyone said this, but this is a very influential paper where people talked about the idea that frictional stick slip could be a mechanism for earthquakes. And this paper by Brace and Byerly, shows some stick and slip here. It's this force and some kind of big units of kilobars. And there's an idea that this can explain some things that happen on tectonic plates. But what's happened over the years, in particular, sort of 20 years or more ago, is that there was really just an idea that there were only these 2 modes of sliding. You could either have stable sliding or stick slip, and there was kind of nothing that happened in between. And so in terms of a diagram like this, a stability diagram, there's a hop bifurcation that happens right here as you cross over between these, the stiffness and a critical weakening rate, frictional weakening rate. You basically just have this or that. And that was basically, really what colored the field in a large way. We looked at temperature and pressure. You looked at the phase boundary between stable and unstable sliding, and there was kind of nothing else that went on. And we've realized over the last 20 years or so that there's a lot of more interesting behaviors that you can see if you look at what's in the Earth. And so they have all these names. Maybe you've heard of them: tremor, low frequency earthquakes, slow slip events, precursors, silent earthquakes. There's a kind of name for what I really think is a spectrum of behaviors. Earthquakes on one side, creep events on the other. And here, just to give you an idea, I'm not sure, maybe people know all about this data, maybe you don't. This is the northwest of the US. This is Oregon. This is in December of 2015. This is in March of 2016. These are events that are occurring at about 35 kilometers depth along the subduction zone. And they migrate from here to there. This is 100 kilometers. So, let's say over about a 500 kilometer interval over that period of several months. They're quasi-dynamic. They're driven by the stress concentration at the front. I think they follow linear elastic fraction mechanics and other things. But the speed is dictated by something that's much more complicated than elastodynamics. Here's some numbers. And there's a range of things, right? This is just slow earthquakes. I'm telling you there's a spectrum, so this can't be the only set of numbers. But this is a typical number for a slow earthquake, that it's moving at 1/10 of a meter per second, a few kilometers per day. And the particle velocity, right? So we want to make sense out of the rupture velocity versus the particle velocity. And it goes like that. But there's other ways to think about this. Yeah. They actually occur at a lot of different depths, and I have a slide that will answer that exactly in 2 slides. But these particular ones are occurring at a depth of about 35 to 40 kilometers along the subduction zone at a temperature of about 500 degrees. This is a thrust. This is a subduction zone thrust fault. There's a big plate here, the plate that's subducting beneath North America here, producing all those volcanoes. Yeah.
Where does the North American plate end?
The North American plate is here. This is a little, almost like microplate out here that is subducting beneath North America. The Pacific plate is out to the left of this. Okay, I knew there were going to be things I had to explain, and I wasn't thinking plate tectonics was one of them, but that's good. Okay, in terms of the scaling, and I'll get in a second about where these things happen, but this is a useful plot to look at. This is a seismic moment. It's something you can measure from seismic waves. It is essentially the work of faulting. You can see by units of it. This is the duration of the events, and these are regular earthquakes live here. There's a kind of a moment goes as the duration cubed in a way that's pretty easy to understand. I'm not going to go through it. And then these slow earthquakes kind of live in a different regime. And there's an idea that because there's a scaling relation here, that people have pushed the idea that it's really fundamentally different physics for slow earthquakes and regular earthquakes. I don't think that's true, but I can't really prove it to you. I can just show you it in the lab. You don't need fundamentally different physics. So, okay, so there's this question about where do they happen, and this is a useful plot to look at. It's not the only way to look at this, but it is focused on a subduction zone, right? So this is the ocean. This is a downgoing plate. This is an overriding plate. There's a seismogenic region. So maybe you think of the Tohoku earthquake in Japan, occurred in a huge range in here. And then up dip and down dip from that, there are these slow phenomena. It's not the only place they happen, but it's one easy way to kind of understand. So this is plotted as distance from that so-called the trench right here. This is some characteristic times you can see over there, right? So big earthquakes, even really big earthquakes, are over in a few tens of seconds, maybe 100 at the most. So they're over quickly. But these other events are taking long periods of time. And the question is, how do they work? What are the speed limits that are set for those? And okay, so now rather than just jump into my own experiments on this stuff, I thought it'd be useful to kind of, paint a picture of the community that I live in and how people think about these problems. And I thought, okay, useful to do it in the context of this problem in terms of minimum requirements for a friction law for faulting. So obviously things could be more complicated than this, but in my view, you need at least this. You need aging, you need velocity dependence of some sort, and then you need to be able to produce repetitive stick-slip motion, right? Earthquakes happen repeatedly. They happen repeatedly on the same fault. So if you have a mechanism that only describes one, okay, fabulous, but then what do you do about the next one? So you want to probably integrate that. And some of this can be seen on this one plot. It's from me, but I could probably just point to Jim Dietrich's work in the 1970s and say, a lot of this was motivated by him. And you're going to see some other stuff related to this, maybe from Rob Karpik in the morning tomorrow, about this. I don't these experiments don't work exactly like this, but our experiments work by sliding along, establishing a steady state, waiting for a period of time. Now I'm plotting a control load point displacement here, so all you see is there's some creep that happens while you wait. Then you reload and you measure this peak in friction as a function of that waiting time, and then you come back to the same steady state, hopefully, or maybe it's more complicated than that. But often it's this simple. What you can see is that if you wait 100 seconds and you do it twice, okay, you see repeatable results. That kind of makes life easy, I guess. If you wait 10 seconds, you see less. And if you drive at 3 microns per second, you see something different than if you drive at 1 micron per second. So part of this velocity dependence is simple, and it's shown right here, that at 3 microns per second, the steady state coefficient of friction is a little bit less than it is at 1 micron per second, so it satisfies the so-called velocity weakening character. But then there's this slightly more complicated thing where the aging rate depends on the driving velocity in a way that is, okay, not too hard to understand, but I don't know, it hadn't really been appreciated, let's say at least by me and the other people who reviewed this paper in 1998, that it turns out this aging rate is a function of velocity in a systematic way. That, you know, I'm still in the kind of regime where I'm thinking, well, the minimum requirements for friction, obviously, I haven't even told you about what I'm doing this with. I'm doing it with powders, ground up rock. I'm doing it under conditions that are super simplified compared to a real earthquake, so I at least ought to be able to explain what happens in my experiments. If you normalize that kind of data, you see that it collapses in an interesting way. And there's a huge range of scales here, but make sure you keep track of the facts. So I've waited in some case up to almost a day, not quite 10 to the 5 seconds, but I've waited that long. And I'm driving in some cases at 100 microns per second. So that's what makes this scale look so big. But there's aging in here, there's velocity dependence. And then if I add in the reproducible kind of stick-slip part of it, here's another plot that I can point to. And again, this is just my data. It's easier to plot. Lots of people have shown things like this. But here is a stick and slip procedure that's going on, driving at 10 microns per second. So each one of these is a little laboratory earthquake. You hear them. There's acoustic coupling. They happen quickly. And what happens when you drive faster is you get a systematically lower stress drop. Now, these are not exactly reproducible because it's a complicated system. But if you look at the systematics, you see something that's kind of understandable. In fact, it's something that I showed you in the very first plot that I started out with. So it's something where we are going, that there's velocity dependence to the stress drop in a way that would allow you to, I don't know, let's say reproduce earthquakes in a model like Jim Rice has done many times. And it's kind of pioneered the idea of, but also maybe understand something about the underlying behavior. So, okay, so I'll do 2 other kind of quick things before I talk a little bit about what we're doing with slow slip. And these rate and state laws came out of Jim Dietrich, Andy Arena. Jim Rice had a lot to do with the early stages of them. What you see in them, in my view, I don't know, I don't need to go through all the details. Probably you already know. If you don't, I'm not going to be able to tell you in 1 minute anyway, but I can show you one interesting thing. And for me, I'm just going to show it to you relative to a paper you might have read from 1951 about the transition from static to kinetic friction, right? Ernest Rubinowitz asked a question about how, if you had this difference between static and kinetic, how do you get from one to the other? And you can see part of that right here, and it produces something interesting when you think about perturbations in normal force. What I've done here is to just sketch out what happens as a function of an increase, a step increase in normal stress to the shear stress. So I'm driving along here theoretically at 100 MPa. Actually, this is from real data, but and I'll show you in a second. But right now, just imagine jumping from 100 to 101. Well, the shear stress is going to go up. Coulomb told us that in 1785. The shear stress is going to go up, but it goes up over some time interval. And it has to go up that. It takes a while for it to go up a little bit based on this idea of a slip weakening kind of model. That you can't transition from one state to another instantaneously, but you actually have to accumulate some displacement to do that. So if this is my displacement plot for that velocity step, if I think about what that means right here, there's obviously a connection here, right? And in fact, the connection was predicted very nicely in this numerical study by Hugo Perfettini et al. And Jim Rice was involved in this. It's published in 2001. What you can see, there's the prediction. And I've just kind of buried the details of the friction response in here. These are the friction parameters that describe the rate at which friction decreases with sliding velocity. And what you see here is that when you drive slowly, you see the shear. So this is shear stress normalized by normal stress. It's like you think of, normalized by an expected value. And what you see is that as you drive at higher and higher frequency, you don't see any response. And the same kind of thing happens here. Well, it turns out we were doing some experiments like that around that time. Margaret Beshew, who's super capable of doing interesting things, and she produced this plot that I think might show pretty much what you need to know. Shear displacement. This is a continuous stress axis from 0 to over 100. There's the normal stress. So the normal stress is just 100 MPa in this experiment, and then we're going to oscillate on top of that at different periods, different frequencies. The amplitude is always 1 MPa, and here's the shear stress response, right? So this is a coefficient of friction of about 0.6, a pretty standard value for rocks. And you can see that for some of these oscillations, something interesting happens, and it's a little more complicated for others. Of course, it's easier if you zoom in, and Margaret was a super talented person and could stand on her hands. So useful to look at her there while you're looking at this. I've just broken this plot up into two pieces, and for me it's easier to start here. I think it's easier to imagine, so here's a 20-second period oscillation in the normal stress. And if you oscillate the normal stress slowly, the shear stress just follows it. There's no phase lag or anything else. The shear stress just follows it exactly like Coulomb would have told you it would. But as you start oscillating at shorter and shorter period, you see that there's a decoupling. And eventually you get to a period of 1 second where you're oscillating so fast that you haven't accumulated enough displacement, right? So I think back to what Rabinowitz told us. We don't accumulate a certain amount of displacement. We can't change from one steady state to another. So he says, so you can see that as you cross over this period, you stop following what's going on. And in fact, in between, so this is sort of an extra thing, but it's more of that data right here. But in between, there's a predictable phase lag between the friction response or the shear strength response and the normal stress forcing. Okay. So, all right. So, for me, it comes back to, why do we use the laws that we use? All right, because we think of these as sort of the minimum requirements, right? They are the minimum requirements to describe what we've been doing in the lab. I don't guarantee that they're right even exactly for the lab. They roughly work. Certainly don't guarantee they work exactly for earthquakes, but they allow us to sort of play the game of connecting with some earthquake-style data. So now, what about slow earthquakes? Well, all right, so we've known about slow earthquakes in Fault Creek for a long time. This paper was published in 1967, but in the fine print here, you see that in 1956 and in 1960, people discovered a creep-style motion in an area, the Cienega Winery, just south of San Francisco in California. And in fact, you can still go there. I think there must be some correlation between this creep mechanism being discovered there and wine. I'm not sure exactly what it is, but you can kind of think, they were drinking wine, they were creative, they were thinking carefully. They saw offset of this house, and so we've known about slow earthquakes for a long time, but we haven't had much of a detailed appreciation for the way they work. So maybe I've done some of that already. What I really want to do is talk a little bit about the mechanisms for slow slip. How does it work? What sets the speed limit? And I'm going to do it by making an analogy with the lab experiments that we do. I'm going to show you some results from double direct shear configuration. Allows you to kind of make close measurements. We often shoot acoustic waves through them while we're measuring. Measure things to a fraction of a micron usually. And so we have a good system for making careful measurements. We work in a regime where the loading system is super stiff normally. And we work in a regime where the whole block slides at once. So at least at the normal way that we measure it, right? We don't see all the kinds of things that you're going to hear from Ely and that started with Shmuel and various other people here that we can image the way the rupture works. We are simply looking at the macroscopic friction and observing some things about it in the context of this double direct shear configuration. This is a standard thing that you see. Load point displacement is a function of shear stress divided by the normal stress. It's kept constant. Driving along, we see a peak stress. This is for a layer of quartz powder to simulate a fault gouge. And what we figured out we could do, first by accident, and then we looked into it and understood that we could find a transition from stable sliding to growing perturbations that reach the kind of limit cycle. These are all stick-slip events. These are actually slow stick-slip events. And you can see that these little perturbations in here, first they're in the noise and they're going to grow. And over a period of sort of 10 to 20 of them, they grow into this roughly stable configuration. These are not exactly the same, but they're roughly stable. If you look at the details of them, you can see, we have pretty good, careful measurements of what happens. We see the full acceleration history from the stick part, where it's just sitting there, to the slip part. And if I focus in on the time part of that, it looks like this. So this is, 5 times 10 to the minus 3 in friction. This is 20 seconds. So there's sort of the noise in them. This is how fast they accelerate. And if I blow up a couple of them, here's the acceleration history. So I kind of, I have a pretty good idea about what happens in this system for this set of configurations. And for each one of these stick-slip events, I can measure the local elastic stiffness, right? For my apparatus, obviously I know what that is. But then I also have to account for the stiffness of the actual layer that I'm shearing. So I've got all that. And thinking to myself, if I slow down for just a second, there might be a question. Perfect.
What do you do to get into this?
That regime, so that was all just one normal stress. And yeah, what I do is to get close to the stability boundary. And that's what I'm going to show you, like how I know that. Because really, initially, we sort of just figured it out by accident. It took us a while to understand what was going on. And you can see part of the answer right here. So that was an experiment that was run at a single normal stress. It was 8 MPa. Here's different normal stresses going from 6 to 14. And they're all, this is time and friction. I've just offset friction here so you can see all of them. If I normalize the stick slips that happen from 14 to 6, I see a pretty big difference. Like this, at 14 MPa, these are real acoustically coupled stick slip events that happen in a millisecond, typically. You hear bang, bang, bang when these happen. You don't hear anything here. This is taking place, the stick slip, so these are all normalized on 0 here. The stick slip happens over almost a full second. And if you look carefully at the acceleration history, you realize this stick slip event reaches a maximum velocity of 80 microns per second. We're driving this thing at 5 microns per second. So it's observable, it accelerates, but it never goes very fast. And so now, to answer Jay's question, I guess 3 or 4 slides to do so. And where am I on time? I got time. Okay, good. I like that answer. Something. These are slow events. These are fast events. This is normal stress. This is the way I'm producing them. This is load point displacement. So I see some simple things. I get small stress drops for low normal stress. And actually below this, I don't get any stress drops. So right here, I've gone through the stability transition in terms of the control parameter of normal stress. Now, nobody's asked so far. Maybe it's just because you're all too polite. These things here are not just weird noise in the experiments. These things here are where we stop the experiment for a couple minutes to reposition a control transducer because we're too cheap to buy a bigger one, or we're too worried about losing dynamic range, so we want to have careful measurements. So we stop and move this control transducer, and during that time we have done basically a slide, hold, slide style test. We've waited a few minutes, and after we start driving again, we see evidence of that because there's an increase in the strength. So these are perturbations. Then you can see, the evidence of them, the effect of them doesn't go away instantaneously. It goes away over a couple different stick-slip cycles. So a bunch of interesting things, easier to look at if we normalize. I mean, I showed it like this because I think, all right, so Coulomb told us this. At higher normal stress, we're going to get higher strength. And we can see this stability transition going on. So if we focus on the friction, so I've just arrayed the curves here to look at them. They're all shown on this pretty small scale, right? So that's 0.05 in friction. They're all shown on the same displacement scale. And you see an interesting set of behaviors. You see typical stick slips up here, and I'll show you the details of them here in a second because I'll pull out the characteristics of them, the maximal particle velocity, the durations, et cetera, the stress drops. But just for now, you kind of see, and you can see that the transition here, you can see it takes longer, more displacement to produce the transition at lower normal stress. Below 6 MPa, we don't even get a stick slips. You see period doubling in here. Very nice examples of it here, and then it transitions out. You see more of that here and here. You see this long period oscillation of the modulation of the stick slip stress drop, and sort of, there's a bunch of complicated things that are happening in that regime. And in terms of trying to, sort of piece it together, one of the simplest things you can do is just look as a function of low to high normal stress. Right now I'm just showing it to you like this because I haven't measured anything for you yet, and I'm going to do that in a second. But these low normal stress stick slip and creep slip events are pretty slow, right? So these are 60 micron per second. I'm driving at 5. These are starting to be pretty fast, right? So we can make even faster stick slip events. We can make stick slip events in the lab that have the particle velocity of an earthquake was up to meter per second, but we were focused on this regime. We didn't keep going in that direction. These are already fast enough. You hear them bang, bang, bang. And down here, it's the stable sliding. So we've kind of gone through the stability transition. And
These gaps.
gap where?
You have like blobs or what?
Yeah. We
At
have,
the bottom, like you have empty zones.
yeah.
Real?
Yeah, so you can see a little bit more of it, but I think it's a good question. I've often wondered myself, like, yes, I say it's a spectrum of slip behaviors as if it's continuous. Not 100% sure that it is, but these gaps are simply, chosen by the normal stresses that we chose. Just we only changed them in that data set 1 MPa at a time. So there's a lot more that could be in there. There's another.
Velocity is identical for all the experiments.
Yeah, the driving velocity is the same for all of those. There's a longer version of this story that says that when we were first figuring this out, we started to figure it out as I went on sabbatical, and then I was going on sabbatical to help build this instrument in Rome that got working right away. And we did the same experiments in Rome. The stresses are different because the fundamental stiffness of the machine in Rome is different. And the sample size was slightly different. But it was different in a super predictable way. We expected it after we looked at the Penn State data to be at 13.7, and I think it happens somewhere between, like 13.7. This is what happens at 25 there. This is what happens at 15. You can see this long period modulation of the stick slip again. You can see at 13.5 and 13, kind of nothing happened. And there's the same kind of data. So, yeah, I don't know if there's some holes in here, maybe there are. I haven't really ever looked carefully at that. There's certainly holes when you look this way, and I think that's just because, the stress drops are. This is only the cases where we had good enough data to actually say anything about what the peak velocity was in millimeters per second. Okay, so there's interesting systematics here. I'm not going to take time to go through all of it, but in fact, this is exactly what happens in slow earthquakes in nature. Slow earthquakes have small stress drop compared to regular earthquakes. Regular earthquakes in nature typically 10 MPa or so, maybe 100 MPa in rare cases. But what you see here is that as you get to smaller and smaller stress drop, you go to the longer duration events. Free event. Okay, perfect. So, without all the details here, let me just say that, Jim early on predicted what the critical stiffness should be in the context of these rate and state laws, and there's a version of it. It is the rate of weakening, this B minus A term, divided by this slip weakening distance that came fundamentally from Rabinowitz. This is the first order term. If we want to make this stress per displacement, normalized by normal stress. And then there's a correction that has to do with an acceleration term if the mass and velocities are big. And I would say, actually you can plug in numbers and see this term doesn't matter for us because we're in the regime where we're trying to understand what happens at tens of microns per second. So whereas this was the original view, we're seeing something more complicated. And actually something more complicated was predicted here for a certain kind of friction law. So pay attention to this for a second. This is slightly below k over k sub c of 1, the permanently sustained oscillations. But then pay attention to this too. This is the velocity jump ratio. They're tiny little velocity jumps that make this happen. And bigger velocity perturbations produce instability in that model. And that was just for one style of event. Okay, so now what I'm going to do in like 3 slides instead of 6, I think I had roughly planned here. I want to convince you that I know what k over k sub c is because I've shown you all of this, and I've shown you how that varies, and I haven't shown you k or k sub c. So let me show you k very quickly. I measure k in 2 different ways from experiments like this. And here I'm just going to show you k because I think in terms of friction. So I want to think of that critical weakening rate in terms of b minus a over d sub c. I'm going to forget about the stress part of it. It is this number, 4.5 times 10 to the minus 4 per micron with some noise. Okay, here's what k sub c looks like. So I know how to measure d sub c as a function of shear displacement. In fact, we've known this for a long time as a community, that this was what happens in our experiments as a function of shear fabric development. So I also know how k sub c changes as a function of shear displacement in my experiments. And what you see is something that looks like this. So this is a sketch. This shows units of stiffness. Of course, real stiffnesses have to be positive here, but this critical stiffness could be negative if b minus a starts out being negative, and it does. So this is what's happening in our experiments, and we can see numerically, almost exactly when it happens. We can understand why there's a normal stress dependence to this transition, because there's a normal stress dependence to this transition in terms of k sub c. This is a slightly complicated plot to look at, but it's like the sketch I just showed you. Higher normal stress produces a lower value on this because I've normalized the stiffness by the normal stress here. 15 MPa looks like this, 35 looks like this, and I presume that the k sub c term doesn't change much in the regime that I'm looking at. So I know what k over k sub c is. I know where I am. And here's the numbers that we measure. Here's the same data I showed you before. So this transition from stable to unstable happens basically exactly where you expect it to happen, and kind of exactly where it was predicted to happen by this. Now, there's a slightly longer version of this, but I'm just going to skip, because the only other thing I was going to show you is, let's see, I guess I was roughly there, so maybe I can just show you 2 more slides. There's another slightly more complicated thing that goes on that was also observed by Heslow and Baumberger in 1994, working on some paper experiments. They showed that when you're near the stability boundary, you can also cross it in terms of the driving velocity. And it turns out that works very well for our data too. So this is what they showed, is what we kind of see, that if you're near the stability boundary here in terms of stiffness velocity, you can drive across into stable sliding by just going faster. And we have detailed measurements of it, but you can see it all in one kind of noisy experiment right here, where when you go at 10 microns per second, you're unstable. When you go at 110, you're stable and noisy. And when you're at 30, you have smaller stick slip events. So I guess bottom line, in a sense, in the lab, we can produce this range of behaviors that corresponds, I think, to the range of behaviors that you see in nature. And we have a pretty good idea about what's going on with it. In the lab, at least, it's possible to say that near the frictional stability boundary, the fracture energy becomes approximately equal to the energy release rate. I didn't show you that, but we can measure this in our experiments because we know what the stress drop is and we know what the distance is over which that happens, so we have a rough idea about what it is. There's some idea that this critical frictional weakening rate could be a function of slip velocity in a way that Baumberger had also discovered. And then ultimately, the stress drop is complex when it's low. And so I think there's a lot more to do here, but there's an opportunity now because of the way these experiments came together to really kind of dig into some details about what goes on with this transition and the slow modes that happen in it. So I'll end there. Thank you, Jay. Happy birthday, Jay.
Any questions?
So,
Chris, could you comment or give us your view what happens on the fault zone in terms of physical processes on the fault zone during the stick slip of the slowest quake versus, let's say, the stick slip embracing violently
yeah.
in a very high confinement?
Yeah, it's a really good question. It'll take me too long to give a detailed answer, but I think the answer for me is basically heterogeneity. It is heterogeneity in the frictional properties or in the initial stress state that stops a slipping patch from getting big enough to become quasi-dynamic. So it is like my story if you like the idea that you can turn the local stiffness if you can connect it to the size of the slipping patch. And I think what happens when you transition from the traditional seismogenic zone to below it is that you go through this region of heterogeneous behavior where you can't make a nucleation patch size big enough to make it be quasi-dynamic.
In the experiment, what is the scale of this heterogeneity?
So I'm scaling my experiment to nature. In the experiment, I've got control over everything. I can play around with the critical stiffness, and I can play around with my loading stiffness, and so I can see the transition. In nature, I wouldn't be able to play around with the critical stiffness too much because it's going to be dictated by pressure, temperature, chemical conditions, and let's say mineralogy. So I have to have some way of dictating what the local stiffness is around a slipping patch. And I think probably what happens is that heterogeneity is what basically changes K and holds it in the right place.
In your experiments, you use constant velocity or constant force or constant force rate?
Constant velocity. So our boundary conditions are constant driving velocity, and we can vary it. Yes, I showed you for as you change the driving velocity, the stick slip.
And
Yeah.
is that supposed to represent, driving of plates, tectonic plates? 'Cause I've seen in the literature sometimes
Yeah.
the term is constant velocity, and sometimes a constant stress rate, and sometimes.
It's a good question. I mean, my own view is that constant velocity is probably the right boundary condition because the systems are stiff enough for that to be the case. But you can imagine being close into a fault zone where somehow you imagine the compliance to be big enough that the stress is constant over some period of time. But I don't know. Certainly at a very broad view, the plate tectonic rates are just dictated by Euler poles and angular velocities in a way that we don't think it changes in any systematic way. Yeah.
I noticed in the plot with the oscillations, I think it was the handstand slide,
Yeah.
where before the oscillations were slow enough for the friction to follow the stress,
Mm-hmm.
the friction was like it dropped as you were decreasing the speed of oscillations, like
This plot?
at the top there.
Yeah.
Is the friction actually decreasing as you're increasing the period before it starts falling?
You mean like from here to here?
Yeah.
I think that's just a kind of displacement effect in the experiment. It's always tricky in these experiments to kind of, do what you want to do, which is a partial derivative. It's not a cross partial derivative. So I keep all things constant except for the one thing I want to. But yeah, displacement weakening is tough to get at, but there's not much of it here.
Last question, Dan?
Yeah, just curious about maybe minor experimental details of this, just the samples loading the experiment when they're under shear. Are they dry? Don't you control their humidity, their wetness?
We control their humidity. Yeah, it turns out that, and I didn't show you here, but if you actually, well, these are ground up rock. So yeah, we make the samples to be reproducibly consistent. Is that what you mean?
No, I just imagine.
Yeah. No.
Lubrication could change things.
Yeah, for sure. Yeah, and it's something we've known for a while now, that if you look at this aging rate as a function of relative humidity, there's a giant variation in it, and you can't ignore that. So we never run experiments where we don't control the humidity. Yeah.
Absolutely last question. Oh, sorry.
Also experimental question. So you measure the shear stress at the whole load. So there is no problem about wave propagation in the system?
Yeah, so it'd be nice to be able to measure the full stress field as a function of time. It certainly happens in our stick slip experiments, but our stress measurements are made at a kilohertz or 10 kilohertz. And everything's over, within 30 microseconds is the time it takes for these events to propagate across our samples, at least in the fast ones. So it's something we should do more with, but it's hard. If you do the scaling, to get a confined rupture in a rock, you need a sample that's kind of meter on a side. And we don't have one. It's important, and we just haven't measured it. We're looking sort of in, yeah.
Thanks, Chris, again.